Okay, so we're going to talk about graphical representations of vapor-liquid phase equilibrium data for binary systems. Now, if you remember, for a system like that, we've talked about Gibbs phase rule. A Gibbs phase rule tells us that the number of degrees of freedom is going to be equal to the number of components minus the number of phases plus 2. All right, so it's a binary system, so that means our number of components is 2. It's a vapor-liquid equilibrium, so the number of phases will also be 2. So the 2 and the 2 cancel out, and we get that the number of degrees of freedom for the system is going to be 2. So this means that when we specify any two of the state variables for the system, and remember these are things like temperature, pressure, and composition, all of the other variables are defined. So in other words, if we define the composition of both of the species, then we fix temperature and pressure. If we fix pressure and temperature, then we know the composition of both of the species. If we fix temperature and one of the compositions, then we know pressure and the other composition. Now let's take a look at one of the most common ways to represent the equilibrium data for a binary vapor-liquid system, and this is called a TXY diagram. T because on the y-axis we have temperature, XY because the x-axis gives us compositions in both the liquid phase and the vapor phase. Now, the way that Gibbs phase rule works is if we fix two of the variables, the other two are defined. In this case, it's implicitly known that pressure is fixed. So for every point here, pressure is fixed. All right, so we need to know when we look at the data what the pressure is. In this case, this is a pressure of 1 atmosphere. So all these data are for 1 atmosphere of pressure. Then when we fix one other variable, either the temperature or one of the compositions, we know the remaining variables. So let's say we pick a temperature of 80 degrees. Pick a temperature of 80 degrees. You go over to the saturated liquid line. That tells you what the composition is going to be of, in this case, methanol. We've got a methanol-water equilibrium in this case. In the liquid phase. So we go down here and we see that the liquid phase composition is going to be about 25%. Keep following the temperature line over to the saturated vapor line, and we see that the vapor phase composition is going to be a little more than 60%. All right, so pressure's fixed, fix the temperature, get the compositions in both phases. We're only reading the methanol composition off of this x-axis now, but because it's a binary system, we know that the water composition is going to be 1 minus x in the liquid phase and 1 minus y in the vapor phase. Okay, so this would be the other species, water in this case. And that's because we're dealing with a binary system. We can also look at other ways to represent the vapor-liquid equilibrium data. This plot, for instance, shows the data for the same system. So we're talking about water, methanol, vapor-liquid equilibrium at a pressure of 1 atmosphere. Again, pressure is fixed for these data, and I would know that by looking at the caption of the data in my book. So pressure is fixed for these data, and what are shown on the axes here are now mole fraction of methanol in the liquid versus mole fraction of methanol in the vapor. So again, since we have 2 degrees of freedom, if we fix any of the remaining degrees of freedom in addition to pressure, everything else becomes fixed. So let's say we fix the mole fraction of methanol in the vapor at 60%. We would draw a line across to the plot, and we would find that a 60% vapor composition of methanol corresponds to slightly above 20% in the liquid. Now we know the water composition in the vapor because, again, it's a binary system, so 60% methanol in vapor means 40% water in vapor, and 25% methanol in the liquid means 75% water in the liquid. What we've also fixed at this point is the temperature. However, we don't know, looking at these data, what the temperature is. The TXY diagram is more rich in terms of telling us both composition and temperature for a fixed pressure. What a plot like this is useful for, however, is finding the possible combinations of compositions that we can obtain in the vapor versus liquid phase. So this basically tells us the entire space of purities in vapor versus liquid obtainable by the system at 1 atmosphere. To find the temperatures that these compositions correspond to, we would need to go back to the TXY diagram and look up temperature on the basis of composition in the vapor or the liquid. Now, of course, it's also possible to display the data at multiple pressures with a fixed temperature. And doing this will basically show you what varying the pressure will allow you to accomplish in terms of obtaining a specified purity for the separation. So let's take a look at these data now. These data are taken at a single fixed temperature. In this case, the temperature is 150 degrees. Okay, and what we see here is that, again, when we fix a single variable, a single degree of freedom, in this case, the pressure is fixed on the y-axis. When we fix the pressure, since the temperature is already fixed, the system has no remaining degrees of freedom, and the composition in both phases is determined. So let's say with temperature fixed at 150 degrees C, we fix the pressure at 150 pounds per square inch. This will tell us now the resulting composition of methanol in the liquid phase. It's going to be a little bit under 50%. Now, of course, what this plot does not show is the mole fraction of methanol in the vapor. You would need a richer data set in order to find the mole fraction of the vapor, either a plot of vapor versus liquid compositions of methanol at 150 psia or a TXY plot at 150 psia. Okay, so given that the TXY plot gives us the richest data set for looking at binary vapor-liquid equilibrium, let's take another look at a TXY plot. So this is a plot for a different system. Now we're no longer looking at water-methanol equilibrium. Here we're looking at hexane-octane equilibrium. So we're talking about equilibrium between the hydrocarbons hexane and octane, both in their N forms, so they're linear forms. And everything is plotted on the x-axis in terms of hexane composition, because hexane is the more volatile species. So as we have with the methanol water system, we plot in terms of the more volatile species. And then, of course, since it's a binary system, we know the composition of the less volatile species, octane, simply by subtracting the composition of the more volatile species from 1. All right, that leaves us the remaining binary species. Okay, so this plot runs between two values. It runs between the boiling point of pure N-hexane to the boiling point of pure N-octane. All right, so we're running from a temperature of about 155 degrees Fahrenheit, which is the boiling point of hexane, the lighter species, to, at the top here, a temperature of about 258 degrees Fahrenheit, which is the boiling point of octane. And of course, at the boiling point of each pure species, the pure species is in vapor-liquid equilibrium. So in this case down here, you're going to have pure liquid hexane in equilibrium with pure vapor hexane. So we're at a mole fraction of 1, and the vapor curve meets the liquid curve. Same thing over here. At the boiling point of octane, you have pure vapor octane in equilibrium with pure liquid octane. So the composition is going to be 0 hexane, 100% octane, and the vapor and liquid curve are meeting to indicate that we're at an equilibrium of pure vapor and pure liquid. Okay, so the two curves here are the saturated liquid curve and the saturated vapor curve. We read off the saturated liquid curve to find liquid phase compositions. We read off the saturated vapor curve to find vapor phase compositions. You can also think of the saturated liquid curve in terms of bubble point temperatures. So think about the saturated liquid curve as a curve showing bubble point temperatures. What the bubble point is, it's the temperature at which a liquid, as you raise the temperature of the liquid, you'll start to go from a pure liquid to vapor-liquid equilibrium. that vapor-liquid equilibrium is indicated by the point at which the first bubble of vapor forms in the liquid as the temperature is increasing. So that point, just as we enter equilibrium, when the very first bubble of vapor forms in the liquid, we begin to evolve vapor from the liquid. That's referred to as the bubble point. Similarly, you can think of the saturated vapor curve in terms of a plot showing dew points. So the saturated vapor curve corresponds to dew point temperatures. So the dew point is going to be the point at which, the temperature at which, if you have a vapor, all vapor, no liquid, you begin to drop the temperature. As the temperature drops, you'll eventually begin to form droplets of liquid, or dew, and as soon as that first droplet of liquid appears, as soon as you have the initial vapor-liquid equilibrium, you've reached the dew point. So cooling a vapor, the first droplet forms, you're at the dew point. And notice that the dew point and the bubble point are both dependent on composition, right? So as we become richer and richer in hexane, the bubble point drops. We begin to form vapors at lower and lower temperatures, and the dew point also drops. So we begin to form liquid also at lower and lower temperatures. The temperature of vapor-liquid equilibrium decreases as we increase the composition of hexane in the system. Okay, so what a plot like this is most useful for is for calculating the result of a separation. So let's say we start with a liquid of a known composition, and we're going to start at this point A. All right, so at this point A, we're at a temperature of 150 degrees, where we have a mole fraction 0.3 of hexane, so we're 30% hexane, which means since it's a binary system, we must be 70% octane. All right, as we raise the temperature of that system from this point A upward, we're in a pure liquid regime. Until we reach the saturated liquid curve, we're in total liquid regime. There's no vapor present. We are not in vapor-liquid equilibrium. We achieve vapor-liquid equilibrium at the bubble point, which here is B. Okay, so at the bubble point, as temperature is increased, for this composition that's 30% hexane, we will form the first bubble of vapor at this point B, which corresponds to a temperature of about 210 degrees. So you can take this out to the y-axis and find that the temperature is about 210 degrees. Okay, so we are now in vapor-liquid equilibrium. There's going to be a vapor in equilibrium with the liquid. The composition of the vapor, and again, since we're at the bubble point, we form just one tiny droplet of vapor. The composition of that droplet is going to be given by this point, C, on the saturated vapor curve. All right, we say that the liquid is saturated because when we add any more energy, we're going to evolve vapor from it. We say the vapor is saturated because when we take out any energy, we're going to start to form liquid from it. So we're completely energetically saturated in either the liquid or the vapor state, and that's why they're in equilibrium, right? Because we're freely trading between vapor and the liquid. All right, so here you're not going to accomplish much of a separation because you've formed just one tiny droplet of vapor. So in terms of the amount of mass that you're separating, you're not getting much. You know the composition of the vapor. At this point C, you just read down from the saturated vapor curve, and you see that your vapor, if this line were straighter, you would see that your vapor is a little more than 70% hexane. All right, so your vapor being a little more than 70% hexane, obviously your vapor is going to be purified in hexane. You started with a liquid that was 30% hexane. Your vapor is about 70% hexane. All right, so you're purifying hexane in the vapor. Now again, this is not a practical separation because you've got a tiny amount of hexane, but you can keep raising the temperature, and let's say you raise the temperature of the system until you get to this point E. So this point E is right in this phase coexistence region between the saturated liquid and the saturated vapor curves. So you're at vapor-liquid equilibrium, and you're at a temperature now of 225 degrees. All right. So again, we read to the y-axis to find the temperature. At this temperature, you have a liquid composition given by point D in equilibrium with a vapor composition given by point F. All right, so if we go down to the x-axis to read those compositions, we see that the liquid composition is going to be a little less than 20% hexane, and that the vapor's composition is going to be between 50 and 60% hexane, maybe 56, 57% hexane. Again, binary system, so if you're a little less than 20% hexane, you're going to be a little more than 80% octane in the liquid. So we started with this liquid that was 30% hexane, raised the temperature to 225 degrees Fahrenheit, evolved a vapor. The liquid is now depleted in hexane. The liquid is less than 20% hexane, and the vapor is enriched in hexane. The vapor is more than 50% hexane. So we've accomplished the separation. We have two products, each of which is purified in one of our species of interest. The vapor is purified in the more volatile species hexane. The liquid is purified in the less volatile species octane, going from 70% octane to greater than 80% octane. We can keep raising the temperature, go up until we hit the saturated vapor curve, and we achieve at point G the dew point of the system. So at the dew point, again, we've got vapor in equilibrium with just one tiny droplet of liquid. The vapor will have a composition of about 30% hexane, right? Because now we've turned everything into vapor, right? So since everything is vapor, the composition needs to be pretty much the same as we've started with, except for that one tiny infinitesimal droplet of liquid, and you can read the composition of that liquid again off, and it's going to be less than 10% hexane. All right. What's important to know here, and what's an actual value that you'll have to use in a bunch of calculations this semester is the dew point. So you need to know what the dew point is, what the actual temperature at which this composition will reach this final vapor-liquid equilibrium, and here it's going to be about 245 degrees Fahrenheit. If we continue to raise the temperature up to point H, we're in a pure vapor system. There's no liquid left, and the composition of that vapor is 30% hexane, 70% octane, exactly the composition that we started out with, necessarily because we've turned all of the liquid into vapor. Finally, we can use the TXY diagram as a way to calculate the vapor and liquid flow rates leaving the separation on the basis of the inverse lever arm rule. Okay, so in order to describe this rule, let's consider a vapor-liquid separation system. So now we have a feed stream entering a separation drum, right, and coming to vapor-liquid equilibrium at a given temperature and pressure. So there's some liquid at the bottom of this drum, and we pull the liquid out with a flow rate L, and then we pull the vapor out from the space above the liquid at a flow rate V. Okay, so what the inverse lever arm allows us to do is calculate this flow rate V and this flow rate L as fractions of the flow rate F on the basis of where the plots are located, where the points are located at the TXY diagram. So let's say, for example, that we're working at the point E on the TXY diagram. So we've taken this liquid that's 30% hexane, brought it up to point E at a temperature of 225. All right, so at point E, what the inverse lever arm rule tells us is that the ratio of the flow rate of the vapor phase to the flow rate of the liquid phase is going to be equal to the ratio of the line segment DE over the length of the line segment EF. Okay, so the line segments that we're looking at here for the inverse lever arm rule are these line segments DE and then the line segment EF. This one right here. To find the ratio of vapor-liquid flow rate, you take the line segment that's closer to the to the liquid curve, rather. So DE is going to be the line segment closer to the liquid curve, and you divide it by the line segment closer to the vapor curve. And this is why it's called the inverse lever arm rule, because here you have V over L, but on the other side of the equation you have the line segment closer to the liquid over the line segment closer to the vapor, right? And it makes sense that the closer you are to the saturated liquid curve, the more liquid you'll be evolving. So the smaller you would expect this ratio to be. All right, so you want the line segment closer to the liquid to be in the numerator, the line segment closer to the vapor to be in the denominator, and this gives you vapor over liquid. Similarly, to find the vapor flow rate as a fraction of the feed flow rate, you simply take now the line segment closer to the liquid. Again, that's why it's called the inverse lever arm rule, because to find the vapor flow rate, we're taking the line segment closer to the liquid, so that's dE. And we're going to be dividing that by the total length of the line between D and F. So this total line segment, DEF, is in our denominator. All right, and similarly, to find the liquid flow rate as a fraction of the feed flow rate, you're going to take the line segment closer to the vapor now, so EF, and divide that by the total length of the line, again, DEF. All right, so the inverse lever arm rule is going to give you the ability to calculate both vapor and liquid flow rates given the feed flow rate.